We will now go on with the agenda. And our next speaker is Mr. Denis Lehmann from the XIMEA company. And he will speak about X-ray imaging, about camera.
Zero, what are you doing here?
And sensor technology. So, Mr. Lehmann and your colleague, the stage is yours.
Thank you. Zero, what are you doing here? This is my show. Yeah, we're talking about X-ray here, not about robots. Sit down. Relax. So, thank you. Wilhelm Conrad Röntgen discovered something in 1895 that was about to revolutionize the field of physics and medicine. A new kind of invisible light that was able to pass through solid matter. Today, I can only briefly introduce you into the topic, but by the end of this presentation, you shall for sure know, first of all, what are X-rays, how can they be detected, how are X-ray cameras different from optical setups, and finally, how can you customize your X-ray camera such that it fits your application. X-rays, that are photons with a wavelength of 10 nanometers and below. The lower the wavelength, the higher the energy, and the higher the energy, the higher the ability to pass through solid matter. When X-rays are combined with imaging detectors, they allow capturing shadow images of the traversed matter. And the maturity of these systems evolved over time, as you can see. There was the first generation, which were film-based, or let's say X-ray film radiography. And you can imagine that this was quite slow. So developing such a film and even digitizing it takes time. So the second generation devices were a bit quicker. They had this two-step approach. First of all, the image was written onto a cassette. The cassette was carried to a computational unit, was put into a reader and read out at that reader. The third generation was actually the first that really combined computers with X-ray imaging detectors. Because the imaging detector would write the data directly into the memory of the computer. That's also what our cameras do. And then finally, generation 4, computer tomography, adds some more, let's say, application to this, because it does not only create 2D images, but it allows you to create 3D models of your traversed object. And I want to show you what this looks like. Now, this little piece of candy was scanned with a micro-CT scanner made by one of our customers, NeoScan. You can see the scanner on the bottom left. And that image was been taken with one of our most recent cameras. It's the XIMEA MJ150XR camera. Let's have a closer look at how detectors work and what you need to make something like this possible. In general, one can say there's two types of detection systems. First, there's the direct detectors. Direct detectors receive, so to say, X-ray radiation, and I directly transform it into a proportionally sized charge. And that charge is then given to a TFT array, which eventually converts this to a digital number. Direct detection is somehow limited regarding the energy levels. So from my reading from papers, it's limited to like 30 to 50 kilo electrovolts. So if you need higher energy levels, you probably want to go for an indirect detector, which allows higher energy, but has one additional step. And that step is the X-rays are being converted into light, into visible light. And this is being done by using a scintillator material. When X-rays strike at or hit scintillator materials, they emit light at whatever wavelength. I will get to that later. And this light can then be identified by photodiodes and can be turned into, again, a charge and eventually into a digital number. There are various detector types. Two prominent ones are the flat panel arrays, which have big pixels, large field of view, but they suffer from speed usually, so they're not that fast, and they don't have a very good resolution. So X-ray cameras, instead, they have a high resolution, they have an excellent speed, especially the newer ones. And if you combine it with a taper, to which I will come later, you also have a big field of view, so it's a kind of like a good compromise. In general, an X-ray camera, or let's say an XIMEA X-ray camera, looks like this. So at the front, you have a beryllium plate, and you need to know that beryllium is transparent to X-rays, or mostly transparent to X-rays. So X-rays can just pass through the beryllium plate and will eventually hit the scintillator screen, which emits visible light. And that visible light is then being channeled through the fiber optic plate onto the sensor. We also provide a shield, so the tungsten copper shield up front. This is just to protect the electronics and to protect the sensor from the radiation. We will have a closer look at most of the parts within the next few minutes. But before we do that, let's first talk about X-ray applications in general. Because people quite often ask me how this actually works. And they have the impression that they can just take a camera, point it at whatever object here at 0, and we'll see eventually through them. And that's not the case, because the applications for X-rays are fundamentally different to optical setups. For X-rays, you certainly need a radiation source that's external from your camera. The sample that you want to be inspecting will be in between your camera and the radiation source, and the radiation then traverses through the sample and hits the camera front. And then the camera does its magic, as I just explained. Insofar, they are way different from optical setups. For optical setups, the reflected light from large objects, like this tree you see there, is demagnified onto the sensor surface just by changing the focal length of your lens. And for X-ray cameras, there is no lens. So, no lens at the front. So that means the sample must be equal or smaller to the size of your field of view, or the scintillator screen. Other than that, let me say that every X-ray camera is different and usually customized to a specific application. The performance of X-ray cameras highly depends on the balanced combination of the radiation source, the scintillator, the fiber optic plate, and the sensor. Let's start with the radiation source. The radiation source has two factors of interest. First is the focal spot size, and the second is the geometric magnification. They both account for undesired image blur. So just imagine that this little line, do I have a laser pointer here somewhere? I don't know. That this little line is your sample, and DF is your spot size, is your spot, your radiation spot. Now, as you can see, the physical setup and especially the distances are important. The closer I move my object to the screen, the less blur effect I have. So the lower is the magnification, and the lower my magnification, the lower is my blur effect. That's what you see in the formula down there. Also, if the spot size is smaller, my blur effect becomes smaller. Okay, in a nutshell. The smaller the spot size and the closer your object to the screen, the better your image. Now, let me show you the performance factors of an X-ray camera that can be customized to your application. And let's start with the scintillator. The scintillator determines the overall efficiency of an X-ray camera in converting X-rays into visible light. And this is determined by the three factors: the material, the thickness, and the grain size. The thickness, in general, determines the probability that X-rays interact with the matter, so with the scintillator, in that case. And thus, it also determines the amount of light that is being emitted. But it's not only the thickness, but it's also the X-ray energy that has an effect on this. As you can see on the right, the higher the X-ray energy, the less probability you have for interaction. So we must choose the thickness wisely and in accordance with the respective application, just to be sure that this works out for you. Let me give you some more insight on some scintillator materials that are being used. The first of them is, well, let's say the two of them are first gadolinium oxysulfide, I will just say GADOX. And the second is cesium iodide, I will just say CSI. Both of them have a very good light output when they are being hit by X-rays. CSI is in fact one of the brightest scintillator materials known. While GADOX generates sharp peaks, as you can see there in the second graphic, it generates sharp peaks, while CSI generates more like an evenly distributed spectrum of light across the whole spectrum. And CSI has its peak where most sensors are most sensitive, so round about at 585 nanometers. Both GADOX and CSI can be doped with other materials that eventually change the behavior of the scintillator material. Yeah? Those materials that are used for doping are terbium, europium, and thallium. So if you dope it, this is an example for GADOX, you will have different wavelength responses. So as you can see, terbium-doped GADOX has a different wavelength response than europium-doped GADOX. I'll just say GADOX TB and GADOX AU. GADOX TB is roughly at 540 nanometers, and GADOX AU is at 630 nanometers. And that's one of the reasons why we're using GADOX TB for the older CCD sensors, why we use the EU version, EU-doped version, for the newer SCMOS sensors. Because we want to have a best fit with the quantum efficiency curve of the sensor. So, in summary, the scintillator material should match the sensor properties, and especially regarding the quantum efficiency curve. Whoops, I think that's, no, okay. The major difference between GADOX and CSI is their structure. While GADOX has a powder structure, CSI is grown in crystalline columns. And this results in a different light scattering behavior between the two. Powder screens, such as GADOX, they emit light into arbitrary directions. That means the thinner the scintillator screen, the better your resolution. But with thin screens, as we have just learned, the interaction probability decreases. So that means for GADOX, we should be only using it for lower energy, X-ray energy applications and not for the high energy applications, because otherwise we just wouldn't have any interaction probability there. Crystalline grown screens such as CSI are a little different because they act, so the light that's being emitted is kind of like tunneled down the crystalline. So you can say that it's more directed. And as it is more directed, we can make the screen thicker. And when we can make it thicker, it's obvious that we can use higher X-ray energies. Once the light is emitted, it hits the fiber optic plate. Fiber optic plates, as the name suggests, have millions of internal fibers that channel photons from the one end to the other end. They, so to say, ensure that the photon arrives at the right pixel. That means they prevent scattering of light. So while they transmit visible light and prevent scattering, they also have another third feature, which is they shield this electronics and the sensor from harmful radiation. Because high energy X-rays are going to destroy your sensor, and they are also going to destroy your camera electronics. The higher the X-ray energy, the more shielding is needed. The thicker the fiber optic plate, the more shielding you have. We at XIMEA usually try to reduce the X-ray energy for your electronics as far as we can. So let's say 99.5 to even 100%. So we need to vary the fiber optic plate thickness depending on your application. If you require 50 keV in your application, that means we have 3 to 4 millimeters of thickness for the fiber optic plate. While for a 250 keV application, we would even have to go for a 60 millimeter. Essentially, we are using two different types of fiber optic plates here. We have transparent fiber optic plates, and we also have radiation hardened ones. While transparent glass has a great transmission for all the wavelengths that are emitted by the scintillator materials that we use, as you can see in the top graph there, it suffers from the so-called Browning effect. The Browning effect means when glass is being hit by X-rays, it becomes non-transparent over time. So that means after some time, your camera is just blind. To prevent this, we are using radiation-hardened fiber optic plates. But this has a disadvantage, as you can see in the graph below, because the transmission is not as good as for transparent glass. And the transmission gets better the higher the wavelength is. So, and that's one of the reasons why we're using now your europium-doped Gadox for the newer cameras, because the transmission is just way higher. By the way, there are also fiber optic tapers. Fiber optic tapers are fiber optic plates where the input size is larger than the output size. So they are used to increase your field of view in X-ray applications. You remember I said in the beginning, the field of view is your limitation. That's a way to kind of like circumvent this a little bit. The sample is then demagnified onto the sensor surface, and this can be a factor of 2 and even 3. The advantage is you can use smaller sensors and save some money on the sensor, because the sensor is the most expensive part in all of our cameras. However, using fiber optic tapers has a disadvantage. The greater the demagnification, the lower the light transmission. And that means only a small proportion of the light is going to be delivered to your sensor. And to overcome this issue, we use larger scintillator thickness to generate more light. But as you know, this also comes with the disadvantage that the spatial resolution is lower. So, in a nutshell, if you can afford the bigger sensor, go for the bigger sensor. The taper will do the job, but the bigger sensor always has better image quality. There are, of course, other disadvantages, including distortions, blemishes, stray light. Let me keep it short. We can deal with all of them, so we can correct them with distortion correction in our software. Stray light can be corrected even within the fiber optic plates by using different techniques, EMA techniques. I mean, you can look it up or just read it on the slide. My time's almost up, so I'm rushing a little bit here. We also do cooling. So you can cool your camera down to minus 30 degrees, and you can even set this in the API and let the camera control it by itself. The electronics determines your interface, your speed, and your connectors. We provide USB, PCI Express in various connection options, different cabling options. And if you want, we can also provide you multiplexing in form of switches or easy synchronization. The last part of your X-ray camera will be the sensor. And as I said, the sensor is the overall field of view. It determines your application. Your sample must be smaller or equal to the field of view. So your sensor in combination with the taper is as big as it gets. There's no way around this. And it must fit your sample. We do have cameras with 60 by 60 millimeters, which is quite large. We can use a taper on them, so it's 180 by 180 if you're interested. And by this, we're combining essentially all the advantages. Yeah, I know, I'm done. Contact us if you have any questions. I'll be glad to run a project with you, determine what you actually need, and we will make the camera for you or select one of the existing cameras or adjust it just for your needs. Thank you, and you all have a safe trip home tonight.
Thank you very much, Mr. Lehmann, for this nice presentation, very informative and highly visualized.
Bye, Zero.
This presentation can also be used as university lecture. The way you collect the information and systematically arrange them, and the way in presenting was pretty impressive. For me, the most informative talk here within the framework. So thank you very much for that. Unfortunately, we are totally out of time. So if you have further questions about X-ray imaging and this crazy robot here, visit the XIMEA booth and ask all the questions you have. And right now we are at the end of the session, camera technology. Thanks for staying with us here. The program goes on, so save your seat and enjoy the rest of the day. Thank you very much.